Hello. So now let us have the second lecture of our linear algebra series. Last time we ended with the notion of of some theorems on vector spaces. So now we will we will discuss the following topics. So we have the subspace. We have a special subspace, the direct sum, and the sum. And then we go to finite dimensional vector space, vector spaces, and we will maybe touch the notion and theorems on linear independence in preparation for the discussion next time on basis and dimension. Okay. Let us start with the definition of a subspace. So definition, we have a subset U here of our V. Recall that V is our vector space over a field F. This is called a subspace or linear subspace of V if our subset U is also a vector space. And then vector space with respect to the inherited. When I say inherited operations, what I mean is the operations which is defined on the vector space V. Okay. As an example, you can check that the set S defined as the ordered triple in F3 where x1 and here x2 here where x1 and x2 are element of F is a subspace of F3. So we can verify that S is a subspace. No, S is a vector space with respect to the operation on the usual operation in F3. So now we will go to the theorem. So this is the condition, subspace condition. Let me remark before going further that some called subspace, some use the term linear subspace instead of just subspace. So here we have the theorem on subspace conditions for a subspace condition. So subset U of V is a subspace if subspace of V if and only if we have the following. U satisfies the following. There are three. So first is that the identity with respect to a vector addition is in U. And then the second is we have the closure with respect. So we have identity. And then we have if U for all U, V and W in our U, we get the sum U plus V is also in U here. So this is called the closure under our vector addition. And lastly, we have if our for all A in the field F, and for all U in the subset U, we have the scalar multiple of A and U is also in U. That is the closure with respect to scalar multiplication. Okay, so the proof here is you have two-way. So you prove that if it is a subspace, then these three must hold, and then the second one, if these three conditions hold, then we get a subspace. I mean, we get a vector space. I mean, yeah. So this is left for reading. We will apply this theorem when we consider we will show something is a subspace. Okay. As an example, let's consider set V. Let us name this set S. S defined as x1, x2, and then x3 and x4. This is an element of f to the fourth. And then the condition is x3 must be 5, x4 plus b. And then S is a subspace of F4, F4 if and only if our B is 0. So how do you show that S is a subspace? And then how do you show, assuming that F is a subspace, how do you show that B must be 0? Okay, so the proof here, we will start with, suppose, we will go the other way. Suppose our B is 0, then what we want to show is S is a subspace. So how do you show that S is a subspace? Basically, we will use these conditions. We will show that the conditions above holds. All right. So let's start. So now we will show that, of course, B is 0. So when B is 0, then x3 is 0. Then this is the 0 vector is in S clearly. So we have checked that one. So we have x0, we have 0, 0, 0, 0. This is our 0, which is in S. Since B is 0, x3 must be 5 times x4. When x4 is 0, we just have this is easy. Now we want to show the second condition. So suppose that x here and y are two elements of S. So we have x is, let's say, x1, x2, and then we have x3 is just what's x3? 5x4, and then we have x4, and then we get y1, y2, and then 5, y4, and then y4. These two are elements of S. Now, observe that x plus y will be just in the operation. So we have x1 plus y1, and then x2 plus y2, and then 5 here, and then x4 plus 5y4, and then we have x4 plus y4. And then this is just rewriting, although this is very obvious. Then 5 times x4 plus y4, and then x4 plus y4 here. Thus, we get this one is an element of S. So this is the closure is with respect to vector addition is satisfied. Also, if lambda is an element of F, note that lambda x is just lambda x1, which is also in F, lambda x2, and then we get lambda times 5x4, and then we get lambda x4. Observe that each of the components are element of x, and then this one, we can write this as 5 times lambda x4, and then lambda x4, which is clearly an element of S. So by subspace theorem, your S here is a subspace of our F4 box, and then that ends the proof. So that's how we show. Not yet. Okay, the box is not yet. So now the second part of the proof is this way. Suppose that S is a subspace. This part is easy. So then 0 is an element of S. Now we have 0 is equal to x1 is equal to x2 is equal to x3 is equal to x4. Thus, your x3, which is equal to 5x4 plus b. We know that here, this is 0, this is 0, this is 5 times 0 plus b, and this gives us b is equal to 0. Thus completing the proof. So we have shown this this direction, and also we have shown the reverse direction. It depends on you how you will proceed with this proof. The second part of the proof is easy. The first part is like just routine checking. Now, there are other examples that I will just state. The subspace, the set of differentiable function on R is a subspace of the vector space R to the R. This is the function from R to R, set of functions. And then the third example, this example here requires calculus background. Let me erase this background. And then the third example for, I will set R2, but this is also true for R3 with some adjustments. This trivial vector space, the space containing 0 only, R2, these are the trivial, these are the usual, I mean, this one is the use at least these two are always vector spaces. And then if we have also lines, we also have all lines through the origin are the only subspace of R2. We can extend these notions to R3. So instead of lines, we will change it to planes. And then together with lines, of course. So remark, showing all the all of this, all ibig sabihin I when I say all are to the trivial subspace and the lines through the origin are subspaces is easy by just applying the subspace test, but to show they are the only subspaces of R2 is hard, and we will prove that later in the course. First, we will develop some theory. Okay. Now we go to the next concept, sums of subspaces. Of course, there are other subspace like the intersection. So I will leave that as exercise, the union, and then it's not necessarily a subspace, but there are extra conditions so that the union will become a subspace. We will leave that to your homework. So we have, now we go to sums of subspaces. Now, we define, suppose that we have U1 up to UM are subspaces of our vector space V. And then not necessarily a subspace, but subsets. Let's loosen the condition. Subsets of V. And then the sum denoted U1 and then up to UM is just the set of all all sums of the form x1 up to xm, wherein our x sub j is in u sub j for j from 1 to m. Example. If U here is the set with x, then 0 as second and third components in F3. Of course, our x here is in F, and then the second one is 0, y, and 0 also in F3. Of course, y is in F, then u plus w is just the set of x, and then the second component is y, and then the third component is 0. These are in F3. Let me write x and y in F. Okay. The second example, if we have 3, u, w, just 2 again, but let's redefine our u to be now instead of just in x3s, it's in x4, f4, xx, y, y in f4. Of course, our x and y are in f. And then w is just x. Then the second component is just x. The third component is also x. The fourth component is y, also in f4. And then x and y are in f. Then the sum u plus w is just x here, and the set x here, same, and then the other one is we can represent this with other letter, of course. We can say it's a, and then the x plus y, we will represent this with the letter same. let me use different letters. So for x, I will let b let that let's represent this as a, and then this is also a, and x plus y will represent as b, and then y plus y we will represent that as z. Okay, so this is an element of f4 or a, not x, a, b, and z are elements of f. So these are examples of sums. Now we will have theorem on not just subsets but subspaces. Theorem. Now instead of subsets, let us have u1 up to um subspaces of our vector space V. Then what is the result here? Then your u1 plus um is the smallest subspace containing u1 up to um. So the proof, the first part is we will show that this sum is a subspace, and the second part is we will show that if it is subspace, this is also the smallest subspace. But now I will leave some part of the proof as when I say clear, you should verify that. Show that the first part, show that u1 plus is a subspace. So we will show that vector addition, the closure under vector addition, scalar multiplication, and the existence of the zero element. So it's a subspace of V. That is easy. And then the second part is to show that this is the smallest subspace of V containing u1 to um. So the now we will show the smallest. So first is uj is, let me write, smallest subspace. Before showing that this is a smallest subspace, we should verify first that that our u1 to um is contained in the sum. Okay. So the first one show not so observe that uj is in u1 plus um by just getting the components of those, since w in u1 to um, w in uj implies w is in u1 to um, since w is just 0 u1 plus up to, and then we get and then U W here, plus, and then all else 0 UM. Okay, this is just scratch work. This is obvious for all J. Now, suppose that our what? Suppose now observe that uh observe that every subspace of V containing U1 up to UM, the sum, suppose that the subspace containing U1 to UM, not only one but all of them, must contain U1 up to UM. Thus, we get U1 to UM is the smallest subspace containing this U1 to UM subspaces. So this ends the proof. Okay, so that's it. Now we go to direct sum. To define direct sum, we have U1 up to UM sum of subspaces, and then is a direct sum if an element, any element of, let's say this is S, can be written as U1 up to UM, U1 up to UM, where UI is an element of UI, big UI. Okay, that's it. In only one way. Yeah. And then the notation for direct sum is U1 U2 UM. Yeah, that's it. Let us do an example. Example, we have U is just the set of X, Y, 0 in F3. And then, of course, X and Y are in F. And then W is just the set of 0, 0, and Z, also in F3. Now, F3 is just the direct sum of U and W. Okay. Since W, which is X, Y, Z in F3, can be written as XY0 plus 0, 0, Z uniquely in, this is an element of U, this is an element of V. the uniqueness here follows. Now we go to non-example. So observe that, of course, we can write this as a corollary if your UI, if your U1 is just this one X here and then 0 all else, element of F to the N, your X is element of F. Then if you have, you follow U2 up to UN, then F to the N is just a direct sum of U1 up to UM. Before going further, we get a non-example. Suppose we get U, which is X, Y, 0. This is in F3. V, let me call it U1, and then this is U2. We have X. No, let me erase. This is 0, 0, Z in F3. Here, X and Y in F, Z in F. And then U3 is 0, Y, Y in F3. Here, Y is in F. Note that F3 is, yes, sum of U1, U2, and U3. Since if we get an XYZ in F3, we can write X, XYZ as X, Y, and 0 plus 0, 0, Z plus 0, 0, 0. But it's not UF3 is not direct sum of U1, U2, and U3. Since if we get a 0 vector, observe that we can represent this as 0, 1, and then 0. And the other one is 0, 0, 1, and then plus, we get 0 here, and we get -1 here, and then -1. And then also, we can represent 0, 0, 0 as all 0 here. Just supply the missing commas that I. Okay, thus, unique representation, uniqueness of presentation is not satisfied. Okay, hence F3 is not U1, U2, U3. All right, that's it. Let us now go to a theorem about direct sum. U1 plus up to UM is a direct sum if and only if 0 is just U1 plus up to UM, where UI is in UJ is in UJ, and each uj is just 0. Proof. Suppose that this is a direct sum, then the only way to write 0 is by taking all all uj is equal to 0. Now suppose we can write, let me leave the first part. Suppose u is u1 up to is direct sum. Show uj is equal to 0 for all j. Now, this part is easy. Now, suppose that uj is equal to 0 for all j, as stated above. Now, we want to show that u1 plus is a direct sum. That means that we have to show unique representation. Okay? So, let v be an element of the sum, and then write v equal to v1 plus vm, and write v equal to u1 plus um. Now, we get v minus v is 0. We get v1 minus u1. And then the second component is is just plus plus v1 minus v2 minus u2, and then we end with vn minus un, and then each component is now note that your vi minus ui is an element of uj minus vj minus uj is an element of the subspace uj for each j. Then we know that from our assumption that each uj is 0, and then thus we get vj minus uj is equal to 0. This means that vj is equal to uj for all j. Thus, unique representation is satisfied. Okay, that's it for our direct sum. Now, we will go to some theorems on direct sum. So another theorem on direct sum, whose proof we will leave. And then we will continue with the next chapter, the finite dimensional vector space. If we get u and w subspace of v, then u plus w is direct sum if and only if our intersection is trivial or just the set containing the additive identity. The proof here is, again, left for the sake of time. So the proof is the result above deals only with two subspaces. But when you ask about possible direct sum of more than two subspaces, it's not enough to test that each pair of subspace intersect only at zero. So, yeah. Now we will go to the next chapter on finite dimensional vector spaces. Notice that we have less computation here. As I remarked, this is a conceptual course. So let us recall our notation. Our F is just equal to R, or the complex numbers. And then our V is vector space over our space, our field F. And now we will go to the definition of linear combination. Okay, we will set some convention first. This is our convention. Okay. Okay. We will write a list without parentheses. So for example, we have V1 to Vn. We just write it as V1 Vm for the sake of shortcut. This is abuse of notation, but we agree on this first. Now we define a linear combination. Linear combination of the list of a list V1 to Vm of vectors in V is of the form V1 and then sum and then Vm, and then we get some scalar A1 and then Am, wherein Ai is an element of F. So as an example, let us consider vector for element 1, 2, 3 in F3 or in R3. This is a linear combination of 1, 0, 3, and then 2 times 0, 1, 0. Okay, so here this is our A1 and this is our A2 and this is our V1 and this is our V2. This is an element of R3. So this W given by this is a linear combination of vector V1 and vector V2 where our coefficients are given as follows. Okay, so that's it. Now we add extra definition. The set of all linear combination is called the span of V1 up to Vm, denoted span V1 Vm up to Vm. So this is just A1 V1 up to Am Vm, wherein our Ai is an element of our field. F. This is another definition. So we set this so that there's no question. So we define the span of the empty list. Empty list. This is empty. Is just the vector, the vector space with 0 as the only element, or this additive inverse. This 0 here is the additive inverse. Additive identity, I mean, of the vector space. And then the next theorem is just similar, with proof similar to what we have shown earlier regarding the sum. The span of a list of V1 to Vn. This is the list of vectors in V, is the smallest subspace containing subspace of course V containing all the vectors V1 up to Vm. The proof is similar with with some. Yeah, the proof is similar with some. Then we get some notation or definition if our span of V1 to Vm is just the entire vector space V. We say our V is spanned by V1 up to Vm, or V1 to Vm spans V. Okay, or V1 to Vm is a spanning list. Let us consider another vector space. So this one, the set of all polynomials with coefficient in F is a vector space. And then another one, Pm, the set of polynomials with coefficient in F of degree at most M. This is also a vector space. In fact, this one is a subspace of the bigger this one is subspace. Okay, we now define a finite dimensional vector space. A finite dimensional vector space is a vector space with finite spanning list. Okay, if it is spanned by finite number of vectors. As an example, Fm is a finite dimensional is finite dimensional. And then it is spanned by 1 x squared up to xm. So there are the number of elements that spans the number of vectors that spans Pm is m plus 1. We now define an infinite dimensional vector space is what? A vector space which is not finite dimensional, meaning the number of the elements in the spanning list is infinite. An example is PF is not finite dimensional. And this course will be focusing on finite dimensional vector spaces only. All right, we are readying our setup for introduction to the concepts of linear independence. Now we go to linear independence or linear and linear dependence. So we get a list V1 Vm in V. Note that I'm defining things here quickly, not really in complete sentence, but yeah. Here V is a vector space. This list is linearly independent if and only if the only choice for A1 up to AM in F, so that 0 is equal to A1 V1 up to AM VM is AI is equal to 0 for all I from 1 up to M. So linear independent. V1 to Vm is not linearly, is linear dependent list if it is not linearly independent. Meaning, we can have 0 as sum of, that is sum 0, sum AI not equal to 0 will give A0 equal to A1, V1, AM, VM. Okay. Next definition is the empty list is we set the empty as is declared. This is a convention, is declared to be linearly dependent. Okay, so if we get an empty list, we say that this is is declared to be not linearly dependent or linearly independent. Okay. I'm messing around with the not. Okay. Now we have set some definitions. We will go to some theorems regarding linear independence. The first theorem is called the linear dependence lemma. Suppose we get a list V1 to Vm, all elements of the vector space V. This list is linearly dependent if there exists a j in 1 up to m such that number 1 v sub j is in the span of v1 to vm, and number 2 if j term is removed, the span of the remaining is the same as the span of v1 to vm, the original one. Okay. So as a consequence of this theorem, we have the following. In a finite dimensional vector space, the length of every linearly independent list of vectors in V. When I say length, I refer to the number of VIs is what? Less than or equal to the length of the spanning list. And another consequence, of course, if we have a spanning list, if there are more than number of vectors than the spanning list, then we get a linear independent list, linear dependent list. So if for it to be linearly independent, it should be just equal to the spanning list or less than the spanning. The number of elements should be less than to that of the spanning list. This one is an obvious fact. Every subspace, of course, because we have a finite dimensional a vector space, then its subspace should be finite dimensional because, of course, subspace is just a substructure of our vector space, the original vector space. The proof here is if you read the book, we just have the steps, and then we build the steps, and then do repeated application of the linear dependence lemma. So every subspace of a finite dimensional vector space is finite dimensional. Meaning there are finite number of element in the spanning list or the spanning set. Okay, so I think the proof here is repetition of linear dependence lemma. The proof is the fact is obvious, but the proof is a little bit wordy. Let me end with the following example. So we get 1, 2, 3, 4, 5, 6, 9, 6, 7, and then negative 3 to 8 is not linear and linearly independent. Why? Since 0, 1, 0, 1, 0, 0, and then 0, 0, 1 spans R3. So the number here, the cardinality of the spanning is here is just 3, and then no list of larger than 3 is linearly independent. So I will leave the other examples and verification as exercise for you. Some of them will be routine exercises, and some of them will be for submission. But that's it. So let me end here. The next topic will be the notion of basis, dimension. So as early notice or early info, basis is just the minimal spanning list, and dimension is the cardinality or the length of the basis. And then we go to linear maps. Some books call it linear transformation. And then associated with a linear map are two subspaces, the kernel, or some people or the book call it null space, and the range space, or some books call it the image. So this is the topic for the next video lecture. So now I'll end here. So I think that's all for today.